Okay, thank you very much, Dawn, and hello, everybody. So my job today is to give you a background in the subject of microlensing in general. We wanted everybody to approach this workshop from roughly the same level, and we don't know how much you've read before. So I'm going to give you a brief introduction to the basics of microlensing theory and the observations that drive it. Okay. So, in the last 25 years, we've found well over 3,000 exoplanets. So the first question that comes up is, why do we bother with microlensing at all? Now, this graph at the bottom starting to give you a clue as to why we look for microlensing at all. You can see that there's a large number of planets that have been discovered, but in this chart, I've plotted them as a function of their separation from their host star. And most of the planets are clearly clustered into this first bump here. There's a second bump that you can see at orbits that are further out, greater than 1 AU, and a long tail extending out here, but you can see that this is not nearly as well sampled. And in fact, this chart hints at that this is not the entire story. The separation as a function of semi-major axis isn't the only parameter in play. Okay. This is a similar plot, but looking into a higher level of parameter space. Here I plotted semi-major axis against the planetary mass. This is a simulation of what we expect planets sample to look like. It's a plot you can see where it's formed a number of different populations that are clearly separated from one another, both in terms of mass and orbital separation, but also in terms of their physical properties, thanks to the simulation. The gas giants are this great big clump at the top. They're relatively easy to find. And the recent Kepler mission has made great headway into finding planets in this region, the rocky and smaller bodies. But there's a separate population that is at further separations from their host star of more ice giant and ice rocky planets. So if we compare that then with the approximate sensitivities of the different planetary detection techniques, you can see why we have this skew in the discovery space. I mentioned the Kepler mission earlier, and there's also been a large number of transiting programs from the ground. They're responsible for that huge cluster of points and that great peak at shorter orbital radii. Similarly, radial velocities are most sensitive to massive but relatively close-in planets. Astrometry we expect to make great headway as the Gaia mission really hits its stride. And direct imaging is another technique which has been used to discover exoplanetary bodies, but it's relatively limited in the number of targets it can look at, and it is, for now at least, constrained to relatively high mass planets that are further away from its host star. And so you can see there's this great big gap, and unfortunately this cluster of blue points largely falls within that gap. And this then motivates the reason for exploring microlensing as a technique, because as we're going to see later in the lecture, its sensitivity falls right over where that cluster of blue points and right within the gap at relatively large orbital separations of around 1 to 10 AU. But it is also sensitive to planets of all masses, so it is sensitive to both the very massive ones and also to the small rocky objects. To prove that this isn't just a theoretical prediction, here's a comparison with the same chart, but with real data. These are the actual planets known to date, and you can see that the impact of the Kepler mission has had and other transiting programs by this great cluster of black points on the left here. The radial velocity is also starting to fill in that large population swathe out here. And sure enough, direct imaging is right at the top corner. Microlensing, you'll see a nice cluster of points, but you'll see that it hasn't quite yet reached down to the relatively low masses. And that's because of the precision, the data precision that we can really achieve from the ground-based surveys. I'll say more about the limitations on that precision later. But we hope to fill this gap in by going to space, and especially with the WFIRST mission, which is why this workshop is so timely. Another reason that microlensing pushes into different discovery space is to look at the discovered exoplanets to date relative to our position in the galaxy. Our position in this artist's impression is this central dot right there, and the planets discovered by direct imaging and astrometry are so close to us in our own solar neighborhood that they're actually within that inner circle, very, very close to us. Transits and radial velocities are able to push a little bit further out. They can go out to 1,300 parsecs or thereabouts. But to put that in context, that green circle roughly represents that radius. And so, as you can see, there's a huge area of our galaxy which we simply haven't yet explored. And there are reasons to think that the planet formation may not be uniform throughout the galaxy. You can see that we know star formation occurs generally in clumps, and that's represented here by some of the red patches. We also know there's planet formation is related to metallicity of the host star, and there is metallicity gradients across the galaxy. And so it is worth exploring a technique that has the capability to look for planets in a channel right the way into the middle of our galaxy. And it allows us to explore a range of different star formation environments. So to recap then, we look for microlensing planets because it fulfills a gap in our current sensitivity to exoplanets, which is actually a crucial population gap. It will tell us a great deal about the total census of exoplanets, and that in turn tells us a great deal about how they formed. And it's capable of exploring for exoplanets in different stellar environments as well as further out into their host stars. So I'm going to show you a lot of diagrams similar to this one. Just to get the caveat out of the way, obviously distances are not to scale, and neither are the sizes of the objects. However, I wanted to give you an illustration of exactly which object was acting at any one time, so I hope they're clear. A microlensing event occurs simply when two unrelated objects line up almost precisely along the observer's line of sight. This means, because the objects are physically unrelated, this is an intrinsically rare phenomenon. And it's the relative motion, or the relative proper motion of both the lensing objects in the center and the distant source that carry those objects into and out of alignment. The gravity of the middle object, the lens, bends the light around itself. As a result, more of the light reaches the observer. This creates two images of the source star. But as they move in and out of alignment, so the source appears to get brighter and then fade again in a very predictable, systematic way. But it's important to realize that we only ever get light from the source. We almost never observe light from the lens. And in this respect, it's unique among exoplanet detection techniques in that we don't directly get EM radiation from anything in the planetary system. And so we don't actually resolve the individual images. Instead, what we look at is the total brightness of the source star as a function of time. And in typical timescale of such an event can span between days up to months. And it follows this very characteristic brightening and fading. For a single lens object, this will be beautifully symmetric. But because it's gravity that's doing the bending of the light, it blends all frequencies of light the same. And so this light curve, unlike most forms of intrinsic stellar variability, will be the same at all passbands. If there's a second object in the system, that second object also has mass and can also lens the background source, in which case it causes what we call an anomaly in the light curve. This can be anything from a slight bump to a very sharp caustic crossing feature like shown here. And the timescale for this kind of planetary anomaly tends to be much shorter, hours to days. And it's easily detectable thanks to this very sharp, bright spike. That's because the amplitude of the signal doesn't depend on the mass of the lensing object, but more it depends on this angular separation of that lensing object from the background source. Because these are intrinsically rare events, there's an incredibly small probability of alignment. This drives a need to observationally look towards very dense areas of sky in order to maximize the number of potential sources in your sample. This is an image on the left taken from the OGLES survey, ground-based survey. And this is to give a zoom in, a typical image of just one tiny 10 by 10 arc-minute field of view within that survey region. And you can see just how dense these star fields are. Every star in that field, its PSF is effectively overlapped by neighboring PSFs. Now, that doesn't mean that those stars are physically lined up. It simply means that the optics within the telescope system, those stars are blended together. The other thing that we contend with observationally is the extinction due to gas and dust, because we're looking right through the galactic plane towards the galactic center. So it's helpful to keep in mind an example of a typical microlensing system. For us, the typical lens that we discover has a host star that is usually an M or a K dwarf, and it typically has a planet orbiting at around 3-4 AU. The source tends to be a background source right towards the center of the gravity, over 8 kiloparsecs away, and the lenses themselves are often quite distant. 6 kiloparsecs is quite typical. And so, to recap the observation section, microlensing depends on the coincidental alignment of two completely physically unrelated stars. The gravity of the intervening body causes the light from the background star to brighten and fade over the course of time, and we almost never observe the actual lensing system itself. Because it's gravity doing that bending, it's essentially a colorblind technique, which helps us to distinguish it from any other types of variability within our surveys. And planets can be found using this technique by looking for clear deviations in the light curve, and sometimes not so clear, as you'll find out. So I'm going to do a brief recap of the basics of lensing theory now. The goal here is to describe the actual lens images that are created of the source. Now, there's a lot of different symbols that are going to be involved with microlensing theory, so I'm going to do my best to introduce you to them quite clearly. And start off with the distance scales are relatively simple. These are relative distances from the observer to the source, to the lens, and the distance between the two of them. Before I move any further, though, it is worth introducing the concept of planes. These are perpendicular to the observer's line of sight to the source, but you will often find us discussing, for example, the lens plane. So we wanted to introduce what we're talking about. The lens plane is simply at the distance of the lens, and you will see quite a lot of diagrams that are drawn within that frame of reference. So general relativity, I'm not going to cover. I'm assuming everyone's had a background into that, but it tells us that massive objects warp space-time, and so a passing light ray traveling close to that object will be distorted as it travels through the warp space. And it's distorted by a measurable angle, which is simply a function of the mass of the lens, ml, and the separation of the ray as it passes the object radially. So, to introduce a few of the angles that we're going to refer to in microlensing, the first of these is the angular separation of the lens from the source. Obviously, this is a function of time as the proper motion carries the two of them into and out of alignment. And at this point, you'll see the first of several health warnings regarding microlensing symbolism. I'm afraid that in the early days of microlensing, no two authors managed to agree on the set of symbols that they chose to use. So if you go back to the original papers, you will often see that they used an incompatible set of descriptive symbols. I'm going to use this set. I'm going to give you warnings of when they might not be consistent with other people. I've tried to keep them as consistent as possible, but I will tell you about the standard set that we now use. For the purposes of the derivation, I'm also going to talk about the angle between the line of sight to the source and the actual light ray, which we're going to consider the path of this light ray as it passes the lens and how it gets bent and into what images this forms. And finally, and probably most importantly, the angle theta between the lens itself and where the light ray passes tells us where we expect the image of the source to be formed. So simple geometry can give us these equations. Theta is simply the sum of alpha plus beta 1. And epsilon, you can see clearly, is simply the sum of beta and beta prime. But epsilon is also a function of relative distance from the lens to the Earth and also from the lens to the source. So that epsilon scales as you move the lens towards or away from us. And so we can express the angle theta in terms of both angle alpha and the physical distances from the lens. Now, bearing in mind that we already have an expression for epsilon based on general relativity, we can consider that for the purposes of microlensing, the lens and the source are so distant that we can use the small angle approximation in basically all cases, and we can substitute for r to give us an expression for epsilon that depends purely on the physical parameters. And from this, we can derive the expression for theta, which depends on just the simple angles and those physical parameters we defined earlier. And this gives us the fundamental equation for microlensing, which is the lens equation, which relates the angle at which the images of the source appear while the source is being microlensed, depending on the physical parameters of the lens, and alpha, which is the angular separation as a feature of time. It has the distinctive property that if alpha is 0, that is, if the source and the lens are perfectly aligned in the sky, then the image of the source that is created has this characteristic radius which depends on the mass of the lensing object and the separation of the lens and source from the observer. This is sometimes written as theta naught, more generally as theta e, because it's named after Einstein himself. And that implies that if the alignment between the source and the background lens is completely perfect, what you actually observe is this Einstein ring, a perfect circle around the location of the lens. I'm going to introduce another quantity at the moment, which is the projected Einstein radius. This is what you get if you project the Einstein radius back to the observer plane. I'm not going to touch on that more in this lecture, but it will come in more important when we reach binary lensing. So it's worth remembering that that is RE tilde. Now, what if the more general case is if the lens and the source are not perfectly aligned but nearby to one another? The lens equation is a simple quadratic, and it can be solved by what you learned in high school. That implies that because there are two solutions, there are two images of the source that are formed during the lensing event. These form close to, but not quite on, the radius of the Einstein ring, and are therefore called the minor image and the major image, respectively. However, theta as an observational parameter is generally sufficiently small as to be unresolvable with most telescopes for most microlensing events. And so what we actually observe is the magnification of the source rather than physically separating the lenses. So looking now in the geometry of the lens plane, I'm going to move on to considering the parameters of a binary lens. This is what we look for when we're searching for planets, of course. When we discover the geometry of the lens plane, we tend to organize the frame of reference in such a way that the binary axis is along the y equals 0 axis for convenience, and the separation between the two bodies is usually called S, but may also be called S0, B, or D, depending on the author. And the masses of the two objects are obviously simply now M1 and M2, but we usually refer to this as the mass ratio Q. Another health warning is that microlensing doesn't measure the exact semi-major axis. What it measures is the projected separation of the bodies at the time of the lensing event. So just be careful of that. It's not quite comparable with the semi-major axis as measured in transit and radial velocity data, for example. Binary lensing can create more than one image if the crucial thing to remember is that the central host star creates two images of the background source when it starts to lens it. If this planet happens to lie close to one of those images, then additional images can be created. And this also introduces us to a different, the one final parameter, which is if we look in the geometry of the lens plane, we could usually consider the lens to be fixed and then the source to be moving relative to it in the background. And so we consider the source trajectory shown by this yellow line. And the angle between the binary axis and that source trajectory is referred to as alpha, and that parameter will be coming back to haunt you when we get to binary lensing in the hands-on sessions. Now, you can imagine that the trajectory of the source relative to the lens could pass through this system at any angle and at different relative rates. And as a result, binary lensing light curves can take on a fantastic variety of forms. This one is a particularly graceful planetary example. Some of them are subtle, some of them are extremely exciting. And so for binary lensing, we have 3 or 5 images. For single lenses, we only have 2. But if a planet happens to be close to one of those, the images of the source during the lensing event, then the image is perturbed and we get additional light, causing a visible anomaly in the length of the light curve. For more information on all of the derivation, you can go to some of the educational materials that we have on the microlensingssource.org tutorial site. To give a background, then I wanted to go through an example of a microlensing system, the kind of typical system that we detect, and what kind of physical parameters that we usually measure to build intuition. So starting from that example that I introduced at the beginning, we have an M. dwarf host star with a mass of half a solar mass, and the source is way back in the bulge at 7.5 kiloparsecs. The lens is somewhat closer at about 6 kiloparsecs. The actual angular size of the Einstein radius is just over 6 milli-arcseconds. And for this reason, it's too small to resolve. Or it's usually too small to resolve, that is. And as a result, you can consider it as a very small cross-section of interaction. For a microlensing event to occur, the source has to pass very close to or inside of that radius. And that tells you how precisely those two objects have to line up along the line of sight. This means that they're intrinsically rare and drives that requirement I mentioned at the beginning towards a dense star field of potential sources. If we compute using the distance of the lens, the Einstein radius as a physical radius instead of an angular one, we can see that a typical Einstein radius is around 3 to 4 AU. That's why microlensing is particularly sensitive to planets that are between 1 to 10 AU, exactly in that region where we're missing a sensitivity gap. Because we detect planetary anomalies if the planet happens to lie close to one of the images and the images form close to that ring, then we are most sensitive to planets that are around that kind of radius. But of course, we don't see the individual images themselves, we only see the overall magnification of the lens as a function of time. In this case, mu-rel is the relative proper motion of the lens and source from the observer's point of view during the event. Given typical movements of stars within our galaxy, the typical timescale, or the Einstein crossing time, is of order 45 days in this particular example. Usually a month or two is quite typical for stellar events. That drives an observational requirement. If we need to detect them, we need to be observing at least once a day. However, we know that theta e scales as a function of mass and also with the distance to the lens and the source. And so if we take our example with the fixed source and lens distances, but we change theta e, we correspondingly change the Einstein crossing timescale. And in this chart, you can see how that scales for planetary masses. That gives us a rough idea of how long we can expect the anomalies to last. And for a Jupiter mass planet, you can see it's of the order of tens of hours, but this drops dramatically for smaller planets. And for terrestrial planets, you can see it drives a requirement to observe less than an hour cadence. Typically, we observe every 15 minutes or better if we can. So to summarize then, these are a few references for the physical derivations that I've been through for reference if you want to go into it in greater depth. Especially recommend the Gould 2000 paper, which gives the formalism that most people currently use. And there is further information and more references on microlensingssource.org. So, the next step of each of our lectures is to finish up with a challenge for you, so to reinforce what we've just covered, but I'll pause here to ask for any questions for the time being before we move on. Everybody asleep? Okay. Okay, so we have the challenge is to see if we can identify planetary microlensing signals. So we've got a few example events for you. And the first up, I'd like you to classify this microlensing event. Your options are single lens, stellar binary, or planetary binary. Hands up first, single lens. Okay, stellar binary? Planetary binary? Oh, good. Very good. Simple, nice, symmetrical curve. The TE is relatively long time scale. Yes, that's a classic single lens curve. This one's a little more complex. Single lens, anybody? Okay. Planetary binary? Two takers, interesting. Stellar binary. Most hands up, that's good. Very good. Yes, there is a clear anomaly in this, and the anomaly timescale is roughly 20 days, which puts it more in the scale of the stellar binary than the planets regime. And so one last challenge. Single lens? No takers, good. Binary lens? Stellar binary? Nope, good. Exoplanet? Yay! Very good. Again, mostly a symmetrical curve. The anomaly lasts approximately 1 day, so that is a classic exoplanet. Okay, and I will stop there. Thank you very much.